Swayam Prabha. Digital India. Educated India.
Hello and welcome to the 18th session of the discussion on machining science course. Now, I will remind you that we were discussing the forces in oblique cutting, and we said that forces or oblique cutting will be different than in the orthogonal cutting, because in case of oblique cutting the tool is inclined to the with respect to the cutting velocity vector. Therefore, the forces are coming in all three axes, and we have to resolve the resultant force into different planes, particularly in the plane of the plane normal to the cutting edge. So, we will look at this slide. For example, here we have determined analytically the cutting force, okay. Fp, this is the cutting force along the cutting velocity vector, and this Fp is equivalent to the cutting force in the orthogonal cutting, we said. So, this we found out, the expression is the following, and this expression can be further simplified by taking that cos nu s. We know that this is 1 plus root over 1 plus tan square nu s. This is the formula that is known to us. Now, the tan nu s, if you remember, we found out the value of the tan nu s earlier, like is this, like here. Tan nu s we said equal to tan nu c sin lambda n divided by this expression. So, this expression we put in the place of tan nu s, and we find that this can be simplified in the following way. So, finally, this is the final expression of the Fp. We can write it in this way, and this you can now compare with the Fc that we have determined in case of the orthogonal cutting during the merchant's relationship, and you will find some similarity, except some terms. For example, these terms will be coming new, okay, because these are due to the tool inclination in the oblique cutting. Similarly, we can find out the Fq, which is the Fq prime, okay, and Fq prime will be r prime sine of lambda n minus alpha n, okay. So, if you remember, in the orthogonal Ft, this is equivalent to Ft in the orthogonal, and Ft was equal to in orthogonal r sine of lambda minus alpha, okay. So, similarly, we are writing here that this Fq prime is r prime sine lambda minus alpha n. If you compare, the Ft was r sine of lambda minus alpha in orthogonal cutting, okay, orthogonal cutting, and here in this oblique cutting it will be r prime, and r prime sine of lambda n minus alpha n can be written as r prime is equal to Fs prime divided by this, okay, or Fs prime can be written as Fs into the cos nu s prime divided by this. Now, therefore, the Fq can be said to be equal to this expression, okay. And the third component Fr is given by Fs prime sin I plus Fr prime cos I, because they are mutually perpendicular. So, therefore, if Fc was equal to, you remember we said that Fp or Fc in equivalent to, this was given by this expression, okay. So, therefore, in case of Fr, it will be Fp prime sin I, Fs prime sin I plus Fr prime cos I, because they are perpendicular. So, similarly, here you put the values of Fs prime and the Fr prime that we found out earlier, and the final expression can be written as this. So, these are similar, right. If you can see that here the Fq, this is the Fr, they are mutually perpendicular. So, they will be all the stress into stress and through the stress and the area, and this is how the expression can be written. And once again I will repeat that here you will find that there is a similarity between the expressions of the FP, FQ and FR in oblique cutting with the FC, FT that we have done in case of the orthogonal cutting. Okay. Now, let us see the rake angles. If the forces we have seen, now how the rake angles can be determined in case of the oblique cutting. Now, here what happens, the basic angles in oblique cutting are the angle ground on the rake face and the tool inclination angle. Okay. Now, since the tool is inclined to the cutting velocity with respect to the cutting velocity vector, therefore, the chip does not flow exactly perpendicular or normal to the cutting edge. It will flow to that side of the normal to the cutting edge where it will get the less resistance to the flow, obviously. Okay. So, therefore, in oblique cutting the following rake angles will be given. Now, what I mean to say is that when it will be flowing not normal to the cutting edge, but inclined and to that side of the inclination where it will get less resistance, meaning that where the rake angle or the inclination of the rake angle will be more than it is made on the actual rake face or the rake face of the tool. So, therefore, in oblique cutting the rake angles are the following. One is the normal rake angle. This is the angle between the rake face and a line normal to the cutting velocity vector measured in a plane normal to the cutting edge. Okay. Another angle is the velocity rake angle. This is definition is the same, that is angle between the rake face and a line normal to the cutting velocity vector, but it is measured in a plane parallel to the cutting velocity vector and perpendicular to the finished surface. And the third angle is the effective rake angle, which is by definition same, but measured in a plane where both the cutting velocity and the chip velocity vectors exist. Now, the angle is the same, but the value will be different because they are measured in different planes. One is measured, normal rake angle is measured in a plane perpendicular to the cutting edge. Velocity rake angle is measured in a plane parallel to the cutting velocity vector and perpendicular to and perpendicular to the finished surface, and the effective rake angle is measured when both the cutting velocity and the chip velocity vectors exist. Okay. Now, let us see, here we will take the tool and this is the projection of the tool here in this plane, all right. Now, this is the cutting edge and the cutting edge is inclined to the normal to the cutting velocity vector by an angle of I. Here we will take the side view. So, this view will be normal to the cutting edge. Okay. If you take the normal to the cutting edge, this you will get this view where this is the rake face of the tool, and if you look at the tool from this side perpendicular to the rake face, you will see a true view of the rake face where this is the cutting edge, okay, and the chip velocity will be along the rake face. Chip velocity will make an angle of nu c with the normal to the cutting edge. In the other view, which is suppose along the VC, if you take a section along the VC, let us say YY, this will be the YY section and here this will be the cutting velocity vector. Okay. Now, here is the chip velocity vector, chip will be flowing along the rake face and this E will be here, the F here will be here in this point at that point, and if we take a section which is along the AE line or AF line, then we will see a view which actually will be true view of the velocity plane, because in here this is called the velocity plane along the chip velocity vector. But here the cutting velocity is perpendicular, here it is not visible because cutting velocity is here in this way. So, therefore, in this view it will be the direction as shown here, this is the VC. Okay. So, this is called the true view of the velocity plane, this is the true view of the rake face, this is the section YY, this is understood, and this is the top, this is the top view, this is the projection of this view given here. Now, from here if you see from the geometry, the sine of alpha e is where alpha e we have to find out in the effective rake angle. So, effective rake angle will be measured in a plane where both the chip velocity and the cutting velocity vector is there. If you see this plane, in here we have the cutting velocity vector here and the chip velocity vector here. In no other plane you will find both the vectors exist. So, therefore, this is the angle which is the effective rake angle, and sine of effective rake angle will be Fe divided by Ae, and from here you find out that with the geometry, that is Fe we are taking from here to here and from here to this view, and Fe can be found out as Fe prime, and Fe prime actually I will show it to you, it is not shown exactly here. So, if you take this view and from here if you take the line, okay, which is actually going to D, all right. Now, this is the intersection which is the E prime. Okay. This intersection, this point is the E prime. So, E prime along this line, along the EF line, E prime is this and Fe prime is this, if it up to E prime. Now, this can be represented as Fe prime is BD here plus E prime we are taking, and then all this geometry. This is not so complicated, like BD and EE prime. If you can see EE prime, this is a small triangle. This EE prime can be represented as DE and the sine of this I, because this angle between this line and this dotted line is the I, okay, inclination angle, tool inclination angle, which is here, because this cutting edge is parallel to this. Okay, this is the horizontal line or the line vertical normal to the VC, cutting velocity vector. So, therefore, from this small triangle you will find out that EE prime is equal to DE and the sine I, this is EE prime, okay. And this then can be taken as BD and the BD plus DE sine I. So, after that it is easy, you can see and compare with this diagram which what is here, and finally what we get is the sine of alpha E will be equal to sine of I, sine of nu c plus cos I, cos nu c, and the sine of alpha n normal rake. Okay. So, this expression is found out from the diagram here and the geometry. This is the simple geometry you can find out from this diagram. It is not very easy, not very difficult, sorry. Now, the velocity rake angle is measured in a plane parallel to the cutting velocity vector and normal to the work surface. Okay. So, therefore, in this plane we can find out that this is the rake angle, because this is the rake face, and the tan of alpha v from this triangle we can find out that this is dB by AB, and dB by AB can be written as this multiplied both sides by CB, and CB by AB will be tan of alpha n normal rake angle, and CB divided by dB will be cos I. Therefore, the tan alpha v can be expressed as tan alpha n divided by cos of the I, that is inclination angle. So, overall you can see that you have to represent the tool in the oblique cutting in this way. It is different because the tool inclination angle is there, and we can find out the relationship between the angles, okay, like in here through the geometry, and the geometry is simple. Once you understand the diagram, that how these angles are derived, particularly these three angles. Once again, this is the normal rake angle. Normal rake angle is measured in a plane normal to the cutting edge, and normal to the cutting edge is that if you take a plane which is normal to the cutting edge, let us say this plane, okay, this is the normal to the cutting edge, and along this plane this will be the view, okay, or this will be the section. Now, since here it is view shown, so therefore, it is not hatched, and in this view or in this section, if it is taken as section, the angle between the rake face and a line perpendicular to the cutting velocity vector will be given as can be considered to be as alpha n, which is the normal rake system, normal rake angle. And the effective rake angle, once again it is the rake angle between the rake face and a line perpendicular to the cutting velocity vector, measured in a plane where both cutting velocity and the chip velocity vectors exist. So, after that it is simple geometry, and through the geometry you can find out the relationship between the angles alpha e and the alpha v. This is the idea of the rake angles in the oblique cutting overall. Okay. I hope this is clear. Although this may be this looks like a little complicated, but you have to understand the diagram. In this diagram overall, once again I will show you that geometry, it may not be very clear because it is not given here, not shown here, not to complicate that. See, this is this factor, right. Fe, this is the projection of E on the line perpendicular to the cutting velocity vector. So, if you extend this line as I said, this line is getting into the D point. Okay. Now, this line is making an angle, this line is intersecting with this vertical line EF at a point which is EE prime. So, EE prime is here. So, therefore, if you see a triangle, it will be something like this. I am just exaggerating that. This is E, this is E prime, okay, and this is D, and this angle is I. Okay. So, from here we are finding out that this is DE sin I is equal to EE prime. This is what we got it here. So, now similarly you can actually look at this expression, look at this derivation from the figure that has been given here, and you can find out easily that how these equation or relationship between the angles can be found out. Okay. Next topic will be economics of machining, and economics of machining, as you understand, is one of the most important factors in machining, because the definition of machining, we said earlier that when we are getting a component, final component with the shape, size, finish and accuracy. What we have not mentioned is that our aim also should be to make a component with a minimum cost or with the optimum cost. So, how to make a workpiece with the optimum cost? That is what we are will be studying in the machining. So, the objective of machining is to produce a component of required dimension at minimum possible cost. The factors that can be varied during the machining operation to change the cost, these are speed, feed, depth of cut, tool and work material, tool geometry, cutting fluid. This we have discussed. Now, the technical data regarding speed, feed and depth of cut are usually not available, and their optimum selection can not be made from the cost consideration only. Okay. Now, an optimum cutting speed always exists for each application, which would mean a compromise between production rate and the tool cost. What does it mean? Let me explain it to you. Like when you are producing at a higher speed, you will always get more material removal rate or less time required for to produce that part. So, your production rate will be higher. Okay. If the production rate is higher, in that case the the profit will be more. But what happens when you are using a high speed, then the tool wear is also very high. So, therefore, you have to use a certain value or certain speed, cutting speed, in which the production tool wear will not be very excessive and the production rate also will not be very less. So, that is what we are calling by saying that compromise between production rate and the tool cost. The cost of machining is minimum at a particular set of cutting conditions. So, it is not only the speed, but it will be speed, feed and depth of cut, and when their values are at an optimum level, then the cost will be minimum, and that is the idea of showing in the economics of machining. For simplicity, we will only consider the case of a single pass straight turning operation and obtain the value of optimum cutting speed. However, you understand that the optimum cutting feed and the optimum cutting depth, that can also be found out. But here for the simplicity, let us explain how to get the optimum value of the cutting speed. Let us assume that we have a cylinder, and in that cylinder the length is L and the diameter is external diameter or outer diameter is capital D. Now, the important cutting parameters are the cutting speed, feed, depth of cut. All right. Now, the technological aspects, they include the surface finish, power consumption, power requirement, force. But the economical aspects will be that what is the minimum production cost criteria, maximum profit rate criteria, and the maximum production rate criteria. So, what I mean is that if we know the important cutting parameters from the machining that we have already discussed, we have discussed the technological aspects, surface finish, power requirement, etc. Now, the economical aspects that we have not discussed we will discuss in the economics of machining, which is minimum production cost criteria, how to select the optimum cutting parameters to have the production cost minimum, or the maximum production rate, how to select the again optimum cutting processes, so that we have the production rate as maximum or the profit rate as maximum. Let us see this. Let us take first the minimum production cost criteria. Let us designate that R, capital R, is the cost per piece. Now, in the cost per piece, we will have the R1 we will designate as the material cost per piece, R2 is the settling plus idle time cost per piece. I will explain what those things are. Well, material cost, you understand that you have a raw material. You are adding value to the raw material to get the final product. Okay. So, that raw material has some cost. This is the R1 material cost per piece. Settling plus idle time cost is that before your machining start, the operator has to set up the machine, set up the speed, feed, clamp the workpiece, okay. And there are some ideal time. Ideal time is that no, this is not ideal time, I am sorry, you please correct it, this is idle time. Idle time is when a machine is not working, okay, machine is idle. Now, like one pass has gone, and in between if the parameters have to be changed, then that machine does not work, but for that time also has to be considered. So, that is called the idle time. So, this is R2, which is settling plus idle time cost. R3 is the machining cost per piece. So, what I mean to say is that everything, all the time that is being spent either for machining or for setting up the machine or the idle time, for all these times we have to pay. So, those costs have to be considered to find out the final cost per piece. Okay. Now, R4 is the cost of the tool changing per piece when the tool is being changed. Okay. Either it can be changed for the regrinding, or it can be changed to have another tool fixed in the tool post, and so on. R5 is the tool cost per piece. Like you have a tool, suppose that tool cost, let us say 100 rupees, let us say for example. Now, with that tool you are machining, let us say 2 pieces. So, per piece tool cost will be 50 rupees, this is an example. TS is the settling plus again this is the idle time, IDLE, idle time per piece. Now, settling plus idle time we have seen here, this is the cost we are taking, but here this is the TS, which is the settling plus idle time, how much time it is being taken per piece. Capital T will take as a tool life, TCT will take as the tool changing time, Tm is the machining time per piece. Okay. Now, lambda 1 we will take as overhead plus labor cost per minute. What is overhead is that apart from the labor cost that you are paying the salary of a worker, you have to pay for the building where the factory is located, you have to pay for the electricity, you have to pay for the water, you have to pay for the hydraulics, you have to pay for the pneumatics and so on. So, this is all everything included in the overhead. You have to also pay to those people who are involved in the design, for example, who are involved in the advertisement, for example, and all those things are involved in the overhead plus labor cost per minute. And lambda 2 is the tool cost per grinding. Like each time it is ground, the tool is being worn out. Okay. So, let us say a tool can be ground 5 times maximum. So, if a tool, that earlier tool which you have taken as an example, if it costs 100 rupees, so per grinding it will be 20 rupees is lost, because 5 times it can be ground, after that the tool cannot be reground. So, this is the tool cost per grinding, all right. Now, frequency of tool changing in producing one piece is, we have the machining time Tm, okay. Tm is taken as a machining time, that divided by tool life will give you what is the frequency of tool changing, how many times you are changing the tool. Okay. With these designations, now we have the cost per piece R. This will be equal to the raw material cost plus settling plus idle time cost per piece plus machining time cost per piece, okay, plus we have R4, we said that this is the tool changing cost of the tool changing per piece, okay, and the tool cost per piece. So, all these costs are to be considered for calculating the tool cost per or cost per piece overall, all right. Now, the material cost, that does not depend on the cutting conditions and remains as a constant. Now, what we are discussing here is that what is the optimum cutting speed that we will be getting for making the cost minimum. Now, in the material cost there is the velocity does not affect. So, that does not depend on the cutting condition. So, therefore, this is constant. Now, the setup and idle time cost, this also is independent of the cutting conditions, okay, because whatever cutting conditions you will have a certain settling time and idle time, and that time we have to pay for. So, that is the cost of that time, and this is not dependent on the cutting conditions. Cutting conditions, we mean to say that cutting velocity, feed, depth of cut, etc. So, R2 is given by overhead that you are paying into how much time you are spending for the settling and the idle, that is the settling and idle time per piece Ts, and for each of that, I mean for that time you are paying the overhead and the labor cost. So, this is lambda 1 into the Ts. Now, the machining cost, this is how much you are spending on machining that particular part. R3 is given by machining time we have, and we are paying for that lambda 1, which is the overhead plus the labor cost. Now, the machining time we have seen earlier that this is equal to length of the length of the workpiece that we have divided by feed and the RPM n. So, that into lambda 1 will be equal to the R3. Okay. So, or this can be equal to Tm is equal to this. Now, for example, the V velocity, this is given as the pi dn, okay, and n therefore can be taken as V divided by pi d, and this for unit change you have to do that, you can do this. So, this will be V 1000 divided by pi d, and we are writing this. Now, the rest of the things or the remaining in the cost analysis or the economics in the machining we will discuss in our next session. Thank you for your attention.